Can everybody hear me up there? Are we good? All right. So today we're continuing our discussion of reducibilities. But first, let's do a quick warm-up on a couple of important concepts. Quick question number one. Is 0 to the 100, 1 to the 100, is that string regular? How many say yes? How many say that string is not regular? How many say that string is not regular nor not regular or regular? It's a string, and string is not a regularity property candidate. Only languages are, and therefore it's a type error I just made, and you fell for it. Okay, good. Any questions about that? So again, you see how easy it is to make type errors. Just be very careful. A lot of you are making these type errors in homeworks, and hopefully you won't make them so much on exams. But a string is not regular, nor is it not. It's not regular and it's not regular because it's a string, right? So only languages have that property. Just like my shoe is not regular or irregular or context-free. It doesn't apply to shoes or to cars, only to languages, these terms. Okay, so be very careful. It's easy to make those mistakes. Okay, second question. Consider the language made up of the string W such that W is equal to the single character 1 if Trump wins the second term, 0 otherwise. Is that language regular? How many say yes? Good, my Padawans. The force is strong in you. Anybody want to explain why that language is regular? Yeah, you can build a pretty straightforward two-state finite state automata would accept this language. It doesn't matter what the condition is. I just picked some arbitrary condition out of the hat, right? The language has one string in it. It's either 0 or 1. There's a simple machine that accepts just the 0 as a language and nothing else. There's a simple machine that accepts just a 1 and nothing else. So there's a machine that accepts this language. End of story, right? So again, just be very rational how you reason about these things. You know, a language is regular if there exists a machine. Doesn't mean you have to know it right this second, as long as it exists. Okay, but it must exist. You can't say, I don't know it, but maybe somebody one day will. If it doesn't exist, it still ain't going to be there, like an integer between a quarter and a third. So wrap your mind very tightly around these concepts. All right, back to reducibility. So we said the concept of reducibilities in the book, section 5.3, pages 206 forward. You should be reading all that very carefully because we only have so much time in class, and it's not very much time, and it's limited, and so I can only say so much, but you need to practice and train on these concepts so it's very clear. So we said that reducibility is basically a mapping from a language to another language. There's a computable function f that maps members of A to members of B, and non-members of A to non-members of B. So it preserves membership through this mapping. It doesn't have to be one-to-one, doesn't have to be onto, but very quickly you can prove all sorts of things from it. So it's called sometimes a reduction from A to B, right? And intuitively what it means is that A is no harder than B. If you can solve B, you can solve A through it, right? So we mentioned an example you're doing right now. You're reducing the problem of becoming financially well off to the problem of getting an education. If you can solve the problem of getting a good education and passing through it and get your degree from a reputable school such as this one, you'll get a good job, you'll be financially well off. So you're trying to solve this problem instead of the other problem directly. Okay, so that's an example of reducibility. Life is full of these examples. And we proved two quick theorems. If A reduces to B and B is decidable, then so is A. And the contrapositive of that, we proved that too, that if A reduces to B and A is undecidable, then B is undecidable also. Then we went through 3 examples. We showed that the problem of halting on the empty string is no easier than the problem of halting in general on arbitrary strings, even though that may seem counterintuitive. How can a tiny little sliver of a subset of a problem be as much difficult to solve as the original problem itself? Well, Here's how, right? A halting problem comes in the door, right? A machine and a string, and you're trying to see if that machine holds on that string. That machine M holds on this string W. But you don't know how to do this, but if you have an oracle for the halting problem solution on the empty string, you build a new machine M prime from this. That's this M prime here. You build an M prime that if you ran it, it'll simulate M on W internally, and you compile this M prime to do that. And so if you feed it to an oracle that solves the halting problem on the empty string, feed it M prime, see what M prime does on the empty string, and it'll do on the empty string what it does on every string. M prime will accept epsilon and any other string if and only if M accepts W. And if you have an oracle to tell you whether M prime will halt on the empty string, that tells you whether an arbitrary M will halt on an arbitrary W through this compilation process. So the process of converting an M and a W into an M prime, that process is F in this picture. That's the mapping F. It's this compilation process. How many get this? Okay, that's a bunch of you. Good. Any questions about this so far? So this is a quick summary of what we did on Tuesday. And then we showed two more results in quick succession, and they looked very much like the first result, almost identical. So the problem of solving whether the language of a given machine is empty or not is again undecidable. Why? Because you can take a machine, an arbitrary instance of the halting problem, M and W, compile it into an M prime that will just simulate M and W internally, and the language of M prime is empty if and only if M would accept W, right? And so if you have an oracle for the emptiness problem, you automatically convert that. If you have a subroutine for the emptiness problem, you automatically convert that into an algorithm for the general halting problem, which we know has no algorithm. It's undecidable, right? Example number 3 consisted on a very similar, again, all these 3 slides, example 1, 2, and 3, are almost identical structures. You know, the only thing that's different is the conclusion, that it's undecidable, but again, you take the halting problem, you convert it into the problem of telling whether a language is regular or not. The language of a machine that I give you is regular or not, if a language has that property of regularity. And basically, if you have an oracle to tell you if a language is regular, you can exploit it into solving the halting problem for you. How? Construct an M prime from M and W such that if its own input X is of the form 0 to the N, 1 to the N, you accept it. If not, you simulate M and W and then accept it yet again if M accepts W. So you either accept everything or you accept only 0 to the N, 1 to the N. In other words, the language of M prime is either sigma star, all strings, or it's simply just 0 to the N, 1 to the N, all strings of that form. In other words, its language is either regular or context-free, but not regular. And if you have an oracle to tell you which case it is, you've solved the halting problem through this oracle. You exploited this subroutine, this oracle, to solve the halting problem for you. So with that, we're about to prove Rice's theorem, which generalizes this concept to the maximum extent, right? So Rice's theorem, you know, is now where we leave the shallow waters and go into the deep waters. So everything up to now was relatively straightforward compared to what's about to happen. So any questions so far? Okay. Yeah.
Can you go a bit more of why you don't even need to run M-prime? What would happen?
So why aren't you running, and why do I keep emphasizing this so much, that we're not running M prime in red and in bold and in large font and in flashing font? Why is that so important that we don't run it? Because the oracle for solving whether M prime, its language is regular or not, it has complete leeway of how to solve it. It doesn't have to run some long simulation. Maybe it has a shortcut. Just like when we try to figure out if this language here on the board is regular, there's a very simple finite automata that accomplishes the recognition of this language. It doesn't have to go through a political simulation of the next 2 years. See what I'm saying? It takes a complete shortcut, short circuits. The whole concept of this condition here, which is a very complicated condition involving millions of people and who knows what else, right? It also involves a lot of media, and it involves a lot of, you know, legal machinations, and it involves a porn star, and it involves lots and lots of things. You know, but I digress. The machine doesn't have to worry about all these nuances and machinations and details. You can just accept this language. And just to be sure, let me write that machine. So here's a machine that accepts language in one case, and here's another machine that accepts the language in the other case. I've written two machines down. One of them does the job. The other one doesn't. But that doesn't matter. I wrote a machine on the board. You're staring at it right now, a machine that does the job. You're also staring at another machine that doesn't do the job, but that's irrelevant. Okay? I proved that a machine exists. So you can take long, direct, you can take shortcuts to a solution that don't involve the obvious way of doing things. So yeah, you can, if you want to know what the machine does on a string, solving the whole, yeah, you can start simulating it. But maybe you don't have to. Maybe there's some shortcut to it. Maybe some very clever algorithm that just looks at the code of M and looks at the string W and somehow infers through some very complex mathematics that we haven't invented yet what it's going to do, instead of just plain simulation. So to answer your question, why don't we run M prime, right? And why do we emphasize that so much? It's because we may not have to run M prime. The oracle supposedly solves that problem. You can look at an M prime and tell us whether its language is regular or not, and he may not use simulation. So the oracle may not run it. He may go through some long, complicated analysis or some short, very subtle mathematical insights that we haven't even invented yet, and we want to give the oracle that leeway to do that. So if we said the oracle must simulate M prime and then it will know what's wrong or what will be the conclusion then? Or if we tried to run M prime and it's inconclusive, the theorem wouldn't be proven. Nothing prevents us from simulating M prime and running it on something or other things or many things. But then you wouldn't have the general theorem that no oracle can do this algorithmically. So we don't want to impose on the oracle how it's going to do its job. We'll just say that algorithmically it somehow solves the problem, whether it wants to simulate it or not. And we show that no matter how it does its job, simulation or no simulation, we can exploit that into solving the halting problem for us, which we know is undecidable. So the oracle can't have an algorithm either. Simulation or no simulation. Any type of algorithm. So for the same reason, I didn't say the simulation algorithm must have binary trees as its data structure, or it may not use simulation, but it must use two-dimensional arrays to somehow represent the data and a lot of linear algebra on top of that. Then all that concludes is that there's no linear algebra type algorithm with arrays that solves the problem. But it doesn't say that nothing will solve the problem algorithmically. So you don't want to constrain it in any way. So we're not running M prime, we're compiling it and then giving it to an oracle. The oracle can do what it wants with it, including simulations if it likes, but we don't impose. Okay, good question. Any other questions? And that question is very important because in Rice's theorem, which is about to come up, we're going to run into this issue again. We're going to construct such an M prime. We're not going to run it. We're going to feed it to some supposed algorithm or oracle or subroutine that supposedly does the job, and then we'll conclude that it can't possibly do its job, at least not algorithmically. Okay, so with this prelude and a deep breath, let's do it. Rice's theorem. So we define a property to be a set of recognizable languages. So for example, property 1 could be all the languages that are decidable. Property 2 could be all the languages that are context-free. So a property has the type, it's a set. A property is a set. It's a set of what? A set of other sets. Each one is a language. So it's a set of languages. A language is the set of strings, right? And a string is a sequence of symbols. So the type of these properties, P1, P2, P3, just its type is a set of sets of sequences of symbols. The type is nested 4 deep. How many understand that? Okay, remember we talked about type errors and nested types and compound types, and I keep reminding you, don't let the types get away from you. Wrap your mind very tightly around what the types are of the objects, right? If you don't know if it's a mammal, you have no way of knowing it's a zebra. Think about it that way. That's why it's important to remember types. Okay, so a language is said to have a property if it's an element of that property, because a property now is a set of languages, a set of recognizable languages. And by the way, a recognizable language is a language that can be recognized by a Turing machine, accepted by Turing machines. It's a language for which is a Turing machine, such that the set of all strings accepted by that Turing machine is that language. No more, no less. By the way, another type error or conceptual error that a lot of people are making in the homework solutions and so on is the language of a machine is all the strings that it accepts and none of the strings that it rejects or doesn't accept, in other words. A lot of people are forgetting that last part, right? So you can have a very simple finite automata of one state that accepts all strings in sigma star. And you can say, well, it also accepts 0 to the n, 1 to the n, because those are strings in sigma star. But the problem with that is it also accepts all the other strings that are not of the form 0 to the n, 1 to the n. And therefore, that machine doesn't accept 0 to the n, 1 to the n, even though it accepts sigma star, which includes 0 to the n, 1 to the n. How many get this point? Okay. It's a very important point, but people keep forgetting that. I mean, think about real-life examples of this, right? Right. So if you say, write a computer program that prints out all prime numbers. Let me show you how I can easily cheat by doing exactly what I just described. I'm going to write a program that prints out all integers in increasing order. 1, 2, 3, 4, 5, 6, 7, all of them. It's easy to do with a single one-line loop. You know, for I equals 1, forever print, you know, I. All right. So doesn't this program print out all prime numbers? How many say yeah? Yeah, of course. What's the problem with this program? Say it loud. It also prints out non-primes. So when I say print out all the prime numbers, you're not going to misconstrue that to mean that you're allowed to print out non-primes as well, because that will trivialize the problem. So you would not make that mistake in a programming scenario or even in real life. Right? But yet, a lot of people are making that scenario, this mistake in the homework, and hopefully you won't make that mistake in the exam. So very importantly, a machine should do what it must, but it should not do anything else. Right? It's important. And you can think about other real-life scenarios where this is true. Right? But anyway, let's leave that at that. But think about that kind of mistakes. Don't try hard not to make them. Okay, so for example, A plus B star has property P1, P2, P3, and P6. Why? Because it's a decidable language. Sigma star is decidable. It's a finite automata that decides it. P2 is a context-free language, also for sure. It's also regular, which makes it context-free automatically. P3 it's equal to its own clean closure. So sigma star, sure enough, equals to its own clean closure. Sigma star is equal to sigma star star. It's already all the strings. So what else are you going to get if you start again? Nothing, right? So P6, it has that property too. It's recognizable. But it doesn't have property 4 because it's not this particular single language, the trivial language containing the empty string. Or it doesn't have property P5 because P5 is the empty property and it doesn't contain anything including this language here. Similarly, WWR, instead of all palindromes of even length, has properties P1, P2, and P6, but not P3, P4, P5. So a property is just a set of languages, recognizable languages, not arbitrary languages, a set of recognizable languages. So a property is trivial if it's either empty or contains all the recognizable languages. So the only trivial properties are these two here, the empty property or the property containing all the recognizable languages, all of them. By the way, are there a countable number of recognizable languages or an uncountable number? Just a quick quiz. How many say countable number of recognizable languages? How many say uncountable number of recognizable languages? Well, we have kind of a split vote. Let me back up. I don't want to be presumptuous. What is a recognizable language? We mentioned that 10 minutes ago, but that was 10 minutes ago, so let's say it again. What's a recognizable language? Language is recognizable if and only if what is true. Somebody say something. Yeah. There's a Turing machine that accepts all the strings in this language. So is a set of all recognizable languages countable? How many say yes? How many say no? Well, now almost nobody is voting. Did I shake your confidence or what? So let me repeat what he said. That a recognizable language is a language that is accepted by some Turing machine. Is a set of languages that are recognizable countable or uncountable? See, by now you should be able to answer those kind of questions in a few seconds. If you studied hard, if you solved lots of problems, you went to the TAs, if you came to all the problem-solving sessions. This is not meant to be a hard question here. I just want to touch base on that fact, and I'm glad I did, because now we're stuck on this, because you're not giving me the right answer. So, set of recognizable languages, countable?
So because the Turing machine's got a finite automata and also infinite state, and the finite automata is kind of like fraction finite, right? And the infinite state, because the state itself is infinite, eventually switches to one string, so there's a finite.
Okay.
There's a countable set of all Turing machines and a countable set of all recognizable.
Yeah, so she's saying the set of all Turing machines is countable. A Turing machine has a finite description. All of its state, its alphabet, its position, it's all finite description for a single Turing machine. So the set of finite descriptions is countable. Never mind the set of Turing machine descriptions. The set of all descriptions, sigma star is countable. And Turing machines are just a subset of sigma star. How many get that? Right? So Turing machines are countable, and so their languages are countable too, because every Turing machine has a language. And there are no more recognizable languages than there are Turing machines, because by definition, a recognizable language has to have a Turing machine that accepts it. That's what it means to be recognizable. So questions like this, really you should be able to answer in 5 seconds or less. A bit of a training tool, advice. Write these kind of things on index cards, 3x5 cards. Shuffle them around, carry them in your pocket. At random times during the day when you're waiting in a line at the supermarket or at the bank or whatever, pull out a card, see, and write down the answers on the back. Pull out a card, look at the question, and within 3 seconds answer it. When you wake up first thing in the morning, all groggy, before you even get out of bed, reach over, take a card, look at it, and answer that question in 3 seconds. Make this question, we just asked one of them, and write down 50 to 100 more. How many are doing stuff like that, training like this? Okay, why not? I mean, if you really want to wrap your mind around this is what you could be doing. And then you'd know this stuff cold. You wouldn't even have to hesitate when you're asked simple questions that are very close to the definitions. Never mind questions that are far from the definitions, right? There are questions that leave the definitions way behind. I'm not even talking about that. I'm just talking about simple definitions and things that are very close to the definitions. Anyway, just my gift to you, try this. It works really well. If you can answer a question in 5 seconds, right, first moment you wake up, you can do it on an exam in half an hour, no problem, trust me. You won't have any issues on homeworks or exams. And you'll be very good at this stuff. You'll impress the heck out of your friends, and you'll impress the heck out of interviewers when you apply for a 6-figure job at Google or Facebook or Tesla or Twitter one day when you're out there trying to impress people. But you need to train like this. You need to think like this, right? You can't just listen to me here for 2 hours a week and then not do much the rest of the time except for a few hours before something is due. That's no way to train. It's no way to train for a marathon either, to run a lot the day before the marathon. So I'm just saying, if it hasn't occurred to you to do this kind of stuff, please do. You have the freedom to do this. And if you do this, you'll be really impressive. Okay. So the 2 trivial properties can easily be solved with a one-line algorithm. Why? The empty property can be solved by a machine that always says no. The algorithm is simple. Print no, quote unquote. And so since there's no languages in that property, no language has that property. And so if you want to ask the question, does the language have that property? The answer is always no. And with a single print statement that says no, you're solving the problem. How many get that? So that is decidable property, the empty property, right? Similarly, the property that has all the languages in it is solvable by an algorithm that just says yes. For any input, you just say yes. So it decides the property for all recognizable languages. You give it a recognizable language, it says yes, and you're deciding the property that contains all the decidable languages. So these 2 trivial properties are both decidable, and not only that, they're decidable with a single line algorithm. They're decidable with a single state finite automata, never mind even a Turing machine. You don't even need a Turing machine to decide those. A finite automata can decide it, and it has one state. How many get both of these things? Okay, any questions so far? Because here comes the hard part after this. Yeah. So he's saying, what if you give it an unrecognizable language? Good question. So we can resolve that issue two different ways. One is you don't give it an unrecognizable language. Because what if we give it a shoe or a car? So if we give it something of the wrong type that it expects, it's kind of an unfair input. You know, what's the square root of my right shoe? Well, it's not 5, I can tell you that much. In fact, it's not even defined. It's not even well defined. So I'm not going to apply the square root to shoes or to cars, only to numbers. And not even to all numbers. I'm not going to apply it to, complex numbers necessarily, or to matrices, right? Or to vectors, or to tensors, or to integrals. I'm going to apply it to reals, right? That's one way to answer that. You feed it what it expects to see. And by the way, how can you give a recognizable language to a machine? How could I give you one on a silver platter? How do you know which one I'm talking about? That's another issue. What do you say to that? So I have some recognizable language in mind. How do I convey that to you? Do I do a little song and dance, and then you infer the language from the way I wiggled around, or like bees do when they want to show other bees directions? Or how do I convey it to you? It's a serious question. Yeah. What's that? I can give you a grammar. Let's be even more direct than that. Write the language out. But what if it's an infinite language? You want me to write out an infinite number of things and then hand that big, heavy, infinite list to you? That forces our interaction to be infinite. Right? How do I, in finite time, convey to you an infinite but arbitrary recognizable language? This, writing it out will work for finite languages fine. It's not a trick question, but somebody got to say something, right? Yeah, just give me the Turing machine. A recognizable language that has a Turing machine accepts it, so fine, give me the Turing machine, and then I know exactly which language you're talking about. And a Turing machine is a finite description, like was said earlier. How many get this? Okay, so why these questions seems to be stumbling points at this point? They shouldn't be, right? They're just definitions, right? If we don't have these definitions nailed down real tight, I'm kind of reluctant to go forward with this theorem, because this starts to stray really far from the definitions. This will get us in deep theoretical waters. And if the definitions are still vague in your mind, there's almost no point to prove a deep theorem using those definitions. You see what I'm saying? That's why I'm kind of pausing here and asking you more questions to make sure it's nailed down real tight in your minds. All right, so back to his question. So the description, the input, better be a Turing machine or something equivalent. Okay. But what if it's not? X can be Shakespeare's Hamlet here. It could be a long string. If you don't like Shakespeare's Hamlet, okay, King Lear instead. Whatever. It's some string that's not a recognizable language. In fact, it's not even a language. In fact, it's not even a Turing machine. It's just some long garbage string. Or it could be long, beautiful, very carefully, elegantly constructed string, like some famous novel or something. But the point is, it's not a Turing machine. It's not a program. It's not a piece of code. It's not a grammar. So how do you modify this algorithm to not say yes to such garbage strings that don't signify Turing machines? It's not hard. It'll take a little bit of doing, but a very simple algorithm filter will filter those out. How would you filter out non-Turing machine descriptions? Instead of a Turing machine, let me ask the question a different way. Maybe you'll see it clearly more then. Instead of a Turing machine, let's specify the recognizable language as a piece of code in Java, the programming language Java. It's equivalent to a Turing machine, right? It's an implementation. A piece of code just basically says inputs and outputs, and you can accept some inputs and reject other inputs, And the language of this program is all the strings for which it accepts. So I give you a computer language, a program written in some computer language, and you want to filter out non-programs, things that are not valid Java codes. How would you filter out non-programs? There's already a famous tool that you've all used many times, in fact, many times each day, that does this exact job, filters out non-programs. What is it called? It's called a compiler, thank you. A compiler filters out non-programs. If you give it something that is arbitrary string or the text of some famous novel, or even a program that has syntax errors in it, it will flag it down, cough it up, and explain to you what all the errors are that makes it a non-program. Okay, how many get that? So you can add some compiler front end here that ignores anything else other than valid descriptions of recognizable languages, whether they're written as code or Turing machines. So you can have a Turing machine and non-Turing machine filter in front of this, right after this arrow here. And if it's a non-Turing machine, you don't say yes, you say no. Okay, and that's one easy way to filter it out. Of course, it's a lot easier to filter out non-Turing machines than non-program. Non-programs, you need some full-fledged compiler-like thing. But Turing machine is such a simple structure that you can, with a few loops and a few case statements, identify anything that doesn't fit the description of a Turing machine syntax. A set of states, a transition function, final states, beginning state, with all the right braces and parentheses in the right places. So that's one way to address this. So I named several different ways to address his question. Very good question he asked. Should give him extra credit just for asking that. You know what? I will give you extra credit. Submit this to the class website as extra credit other, and I want to give you credit for asking that good question. You know, I want to encourage you to ask more questions and not just sit there silently kind of staring at me. That's not, you know, very helpful to you. I mean, I'm having fun, but, you know, I hope that I want you to learn more by asking questions and challenge your minds. Right? Okay, what else so far? Shall we proceed with this, or? Yeah.
Please make the mic louder.
The mic louder? Oh, this is another good comment. Okay, is this getting louder here? Is this good enough? Okay, good. Thank you. What else? We're on a roll here. Okay. So it's easy to decide these two trivial properties. Right? The deep question is, what other properties, other than these two trivial ones, the property that contains none of the languages and the property that contains all the recognizable languages, which ones of the other ones are decidable? And there's an infinite number of ones that are other ones, right? How many see there's an infinity of other properties? Countable or uncountable? 5 seconds, go. How many other properties are there? Countable or an uncountable infinity? How many say countable? How many say uncountable? Whoa, we got a split vote. Which one is it? Anybody want to argue one way or the other? Now, we're not talking about one recognizable language. We're talking about sets of recognizable languages. Countable or uncountable? What do you? Good. Yeah. Yeah. So she's saying that the set of all recognizable languages is countable. We said that 5 minutes ago. You can count the Turing machines, and there you are counting the recognizable languages. But a property is a subset of those. So it's like the power set of all the countable languages, of which there's already an infinite number of countable instances. The power set of that is uncountable. How many get that? Yeah. The power set of any set is bigger than the set itself. It's a bigger infinity. Infinities are not all the same. Some infinities are bigger than others. We've already seen that, right? We didn't used to think that's the case until Cantor shocked all of humanity by showing us that there's many types of infinities, some bigger than others, even though they're all infinite in this very strict sense. So, which properties are decidable of all these uncountable infinity of properties besides those two? Which ones are decidable? And the very shocking, very pessimistic, disappointing answer is that none of them are. They're all undecidable, every last one of them. And we're about to prove this. So far, we proved it for 3 properties. Which properties we proved it for? We proved it for this property, whether a language is regular. We proved it for this property, whether a language is empty. And we proved it for this property, whether the language is the empty, contains only the empty string. A Turing machine only holds on the empty string. So we proved it for 3 so far. But the proofs were so similar that we saw a pattern, and so did Rice back in the 1950s. And basically, he generalized those 3 examples to an infinite number. 1951 is when this happened. Okay, so all the non-trivial properties of Turing recognizable languages are not decidable, every last one of them. How do you prove such a thing? Well, you just generalize the last 3 examples to the general case. This is what we're about to do. So let P be some non-trivial property, we'll just call it P, and assume that the empty language is not one of those languages in P, otherwise substitute P bar, substitute the complement of B for the rest of the proof. Because remember, a language is decidable if and only if its complement is decidable. How many get that? A language is decidable if and only if its complement is decidable. Why? What's the proof for that? If some problem is decidable, why is its complement decidable? If a language is decidable, why is its complement decidable? Yeah, just flip the answer. Flip a yes to a no, a no to a yes, and you got a decider for the complement, right? Easy. So assume that the empty language is not one of those languages in P, otherwise do the rest of the proof for P prime, the complement of P, and then it won't be in there, right? Because the empty language is an element either of the property or the complement of the property with respect to all the other recognizable languages. Okay, so pick some language in P then that's not the empty language, because P is a non-trivial property, so it's not the empty set, and it's not all of the recognizable languages. So there's some language in there that's not the empty language, because we already said the empty language ain't there. Otherwise, consider its complement, and then it won't be there. So you can always find a language in there that's not the empty language. You'll see later why I'm harping on the fact that this language we pull out of P and call L is not the empty language. Okay? But if there's a language that's recognizable, that whatever it is, there's a machine, M sub L, that recognizes that language L. Same is true for any recognizable language. There's a Turing machine that accepts it, right, by definition. Right? So assume towards contradiction that there exists some algorithm or Turing machine that decides this property, that decides, when you give it some Turing machine description, decides whether the machine denoted by this Turing machine description has this property P, yes or no. So we assume that this purple box is this decision procedure or algorithm or piece of code that decides this property P. We'll show in a couple of minutes that this can't exist, right? This decider can't exist, not as an algorithm. Yeah?
Why does the property contain a single finite language?
Why is a property that contains a single?
Like, what if the property is the empty language?
Oh, if the property is just the empty language, why is that not decidable? This is why. Because that's exactly what this example is. This example tells you if the Turing machine accepts the empty, accepts the empty language, the language containing the empty string. The more, I guess, intuitive answer is it's very hard to tell what a machine does or doesn't do. We already know that we can't even tell whether it halts or not, in general, much less what it does before it halts, if it ever halts, or what it does while it's not halting. It's very hard to predict, in fact impossible, algorithmically, to predict what a Turing machine will do, or what an algorithm would do. Not just what it would accept or not accept, but whether it even halts or not. Never mind what else it does. Right? Most of programming tasks aren't even concerned about whether a program halts or doesn't halt. We just assume it halts, and we focus on when it halts, does it halt with the right answer? Does it compute a prime number? Or does it update the spreadsheet correctly, if it's MS Excel? Or does it play tic-tac-toe, if it's a game-playing program? Does it play it well with the player as opposed to making random moves or non-moves? So the bottom line is, you can't algorithmically predict what code does. You can't even predict whether it halts or not, never mind what else it does besides halting or doesn't do. So that's sort of the intuition, and we're about to prove this. So assume that a decider exists that decides that property, whatever it is, as long as it's not trivial. Because for two trivial properties, we already have deciders. You know, there's the two deciders for the two trivial properties, the empty property and the property containing all languages. Those are easy to decide. Because all you got to do is always say yes or always say no, and it'll always be right. Okay, so this kind of goes back to the question that was asked earlier. How do you present a recognizable language to an algorithm or to a Turing machine or even to another person? You can give the Turing machine description, or grammar, or you can give other descriptions are equivalent to that. Yeah.
So you just mentioned that you can't predict the functionality of a program, but what about speculative execution? Is that because it's allowed to be wrong sometimes that it works?
So he's asking, what about speculative execution? Speculative execution doesn't do anything other than tries to save time by executing multiple different possible branches of an if or a case or some other conditional. So you're ready for both cases. It's like contingency planning in some sense. Even in life, you have like speculative planning for contingencies. I mean, that's why you have fire insurance. That's a speculative execution of some plan for something that hasn't happened. Your house burning down. Or some people, speculatively plan or execute plans for doomsday, the zombie apocalypse, right? By hoarding all sorts of things, and if society breaks down, whatever. So that's not hard to do, and there's nothing undecidable about that. But that still won't tell you if a zombie apocalypse will come or not come, or whether a certain branch will be taken or not taken. It just says if it's taken, you've already done the work that you have to do. If it was taken, and then you're good, then you save some time. That's all. That's all speculative execution is. That's all it does. It's about efficiency, not about doing something that you can't do some other way. Okay, so here goes. So we're going to reduce the halting problem to this decider that solves this property. So it's going to be a very similar structure to what we've done before. Right? We're going to have an arbitrary instance of the halting problem. We're going to have a Turing machine, and we're going to have an arbitrary input, a string W. And this instance of the halting problem, we're going to wrap it up into some compiled, not executed, but compiled M prime, such that if we have a decider for this property, it would automatically be exploited into solving the halting problem for us. And here's how it's going to look, basically a generalization of the last three examples. Right? So given an arbitrary Turing machine and a string W, right, that's these two guys, arbitrary instance of the halting problem. We're going to construct M prime. So this is the M prime that we're constructing from these two. We're going to hardwire the M and the W into the finite control, into the constants of this program M prime, such that M prime will simulate M and W. So there's a simulation going on of M and W inside M prime. We're not running M prime. Again, I'm emphasizing one more time that we're not running M prime. We're constructing it. And if it ran, this is what it would do: simulate M and W internally. And if M and W halts, it will then automatically start simulating the machine for L. L is this language that we picked out of the property earlier, a couple of slides ago. That's not the empty language. And if M sub L, the machine of the language L, accepts, we then say yes. We is implicitly this M prime that we're constructing. That's when I say we, I mean it, M prime. So that's how it works. So if M halts on W, it presses the start button of this other machine, M sub L, that accepts the language L, and it fires it up. And if M doesn't accept a W, this start button will never be pressed, and M sub L will never be run, and nothing will be accepted out of the red end of this M prime. Okay? So now, what is the language of M prime? The language of M prime is one of two things. It's either the empty language. If M doesn't accept W internally here, it will never halt, because it didn't accept it. It just runs forever. So if M and W doesn't halt, it would run forever, and this start button will never be pressed. This simulation will never fire, will never fire up and commence, and nothing will ever be accepted that's inputted into M prime. So the language of M prime will be empty, right? On the other hand, if the language, if M does accept W, then this will fire up, and the language of M prime will be whatever the language of M sub L is. And then M prime does whatever M sub L does. A yes becomes a yes, and a no will become a no. So then the language of M prime will simply be L. If M accepts W. So if M doesn't accept W, its language, the language of M prime will be empty. If M accepts W, the language of M prime will be L. And so in other words, M accepts W if and only if the language of M prime has property P. Because L is in P and the empty set is not in P. Remember, to remind you how we constructed this thing, without loss of generality, we assume that the empty language is not in P, which means the empty language doesn't have property P, right? On the other hand, the L was in P, so the empty language wasn't in P, the L was in P, and L is not the empty set. And so if you know what, whether the language of M prime has property P or not, you know whether W halted on, the M halted on W internally inside M prime, right? And so if you had a decision procedure, an algorithm, a way to detect whether the language of M prime has this property, P, you've just solved an arbitrary instance of the halting problem in this process, using this compilation process of M and W, the instance of the halting problem, compiling it into an M prime, and then asking the oracle or the subroutine about M prime, whether it has, its language has this property. And so you've solved the halting problem. And that's the end of the proof, right? And the halting problem we know has no solution, no algorithmic solution, but we just constructed one, so it's a contradiction. And how do we construct one? By assuming that there's a decider that solves property P for some arbitrary, non-trivial property, which means property P is not solvable algorithmically. There is no algorithmic solution for it. But the property P was an arbitrary property. I didn't pick and choose. I said let it be any property you want as long as it's not trivial, which means P was not decidable, which means an arbitrary P was not decidable, which means no non-trivial property is decidable, because P was completely arbitrary property. I didn't specifically single out any one particular property. I made this very general. Well, I didn't do it. Rice did this in 1951. That's his result. I just convey it to you. Okay, this one, I admit, is an abstract and deep result. This is probably the most complicated theorem we've seen so far in this course. There will be ones that will probably be more abstract and more complicated than this. We're getting there. But so far, this one takes the cake. How many get this theorem and its proof? Wow, okay, that's half of you. I'll take it. You know, more than I presumed. That's good. The force is strong in you then. Any questions about this? Up there, yeah.
Why does this proof not work for the everything trivial case?
You mean even for the trivial properties?
Right. You can just use the everything trivial property as P.
Yeah, very good question. He's asking, so I'll give you two. He's asking, first of all, he's asking, why will this proof not work if P was a trivial property, like the empty property or the property containing all the recognizable languages? Very good question. Where will this fail? We know it will fail, but the question is how and where will it fail? So let me give you two answers. The reason it won't succeed in proving that the empty property and property containing all the languages, two trivial properties, aren't decidable is simply because they are decidable. How do we know they're decidable? Because we already gave two deciders for them right there. So that's one answer. The more sophisticated answer is that when you do this and you build this M prime, you have to have a way of distinguishing it its language from being empty to some other thing. And if the property was empty, the language here would be empty, and it would accept the empty language even if this fires up. And it won't just be empty because M didn't halt on W and this was never triggered. This could still be triggered, M can halt on W, and it would still be empty, and you'd have no way to disambiguate these two cases. And it won't tell you what M did on W, because the language of M prime will be empty whether M halted on W or M didn't halt on W. So you won't have a way to disambiguate, and same thing for the other case. You won't have a way to disambiguate the two. And so you wouldn't get some, the universe wouldn't implode on itself, you wouldn't get some big contradiction, you just get a non-proof. It won't apply to that case. I hope that, does that help shed light on what you asked? Yeah. Yeah, so the other case, the language can't be empty. The language of M sub L, the language of M sub L, i.e. L, that can't be empty either. But if the property had all the languages in it, it would also have the empty language as an element. And L could be one of those. And then you'll lose the disambiguation ability again. Very good question, very insightful question. He's asking basically, how can this theorem go wrong? Where will it go wrong if we allow that trivial property to percolate through this chain of reasoning? And that's where it would break, right? On the last step here, you won't get a disambiguation. You wouldn't know for sure which way it works or not. It reminds me of a scene from some famous, I don't know how famous, but some Western movie. Some fastest guy in the West scenario is at the bar. Everybody challenges him, and some punk, gunslinger is challenging this old gunslinger, and he says, son, before you challenge me, I want to show you something. And he takes, a washer, like a metal washer, flips it into the air, draws, shoots, holsters his pistol, and says, I just put the bullet right through the middle of this metal washer. And of course, the young punk goes, wait a minute. And he thinks it's a trick just to stave him off from a confrontation. He says, so the young punk kid says, okay, let me see you do this again. Takes the washer, put a piece of scotch tape over the hole, and says, try it again. And the guy says, okay, and now there's a hole through the tape. And then the young kid says, okay, now I believe you. I'm sorry I challenged you. And he backs away, and nobody has to die. In other words, he found a way to disambiguate whether it was a ruse or real skill there. It was still real skill before. It just wasn't so obvious. Anyway, so you need to be able to disambiguate what's going on here at the end to make it work. What else? Any other questions? So, here's one of the many corollaries of Rice's theorem. The following properties of languages are not decidable. Whether a language is empty, whether it's finite, whether it's infinite, whether it's regular, or we already saw that, whether it's context-free, whether it's ambiguous or inherently ambiguous, whether it's decidable, whether it's equal to sigma star, whether a language contains only odd strings or even strings, whether it's made up of only palindromes or not. Any question, any property about recognizable languages that's not trivial, and all these are not trivial because some languages are regular, others are not. Some contain a palindrome, others do not. Some are the language hello world, there's 2 words. Some are not that language, right? Most aren't. Some are NP-complete, some are not, and so on and so on. And you can make this list as long as you'd like. We already know this list contains an uncountable number of entries on this list, not even a countable number. So any kind of property of languages that you can name, that's not the trivial property, that's not true of all languages or of no languages, and all of them are in this category. They're all undecidable in one fell swoop. We don't need long, complicated proofs for each of those anymore. Rice's theorem covers all of those, and the first 3 that we've seen in the specific examples. So you see how it generalizes the heck out of all these 3 examples and everything else that you can think of, which is amazing. It's probably the most pessimistic result I've ever seen, Rice's theorem, because he says that not just one thing is undecidable, like Turing said about the halting problem. It doesn't just say that a few things are undecidable, like the first three examples that we went over earlier. It shows you that everything is undecidable. Every property in the universe is undecidable, not just a countable number, but an uncountable number, except the two trivial ones, except two. Two, that's it. Out of an uncountable number of properties, only two can be decided. Only two have algorithms. And the algorithms for those two, one line each. So you see how it goes from trivial to impossible in one giant fell swoop. And it's a highly negative result. But it also has positive value in real life. Right? In real life, people have tried to solve many such problems separately. They didn't know that what they're trying to do is impossible. And they wasted a lot of time and energy and money. And some people who are not aware of this result probably still are trying to do that. Build some supercompiler that does impossible things. And at some point, they just have to give up because they will not succeed. Not in general, they won't. For specific instances or watered-down versions, they may succeed. Now, let me give you a very important caveat here. This is about types again. This theorem, Rice's theorem, applies to properties. It doesn't apply to machines directly. It doesn't apply to states directly. It doesn't apply to shoes or cars. It applies to properties. So we're not saying that you can't compute anything in the universe. You can compute lots of stuff. You can add and multiply and divide and subtract, take square roots and run spreadsheets and video games. You can do all that. Your smartphone is proof of that. But those are not properties. Those are certain select functions that you can implement and compute. If that wasn't the case, there'd be no field of computer science, there'd be no programming. Right? If you couldn't compute anything. But there are an infinite number of functions that you can compute. In fact, an uncountable infinite number of functions that you can't compute. And there's an uncountable set of properties that you can't compute either or decide. But Rice's theorem is about properties. So if I give you a Turing machine and I ask you the question, does it have three states, yes or no? How many say, by Rice's theorem, it's not decidable, not computable? How many say it's perfectly computable because it's not about properties, it's about a machine and how many states it has, and you can just count them and tell if it's three or not three. Yeah, that's the case. It's correct. It is perfectly computable if a machine has three states or doesn't have three states. Just count them and then you'll know. So it's not to say nothing is doable, because this is about properties of languages. This is not about other objects, like machines or states or transitions or individual characters or shoes or cars or sealing wax or ships or whatever. Yeah.
In terms of the complexity level from characters all the way up to languages and such, can you count Turing machines as strings?
You can convey or represent Turing machines as strings that give their structure or description. You can also draw a picture of them on the board, like I did with this fine, draw the states, draw the transitions. That'll be a fine description too. Or you can talk about them in English. There's lots of ways to describe something. But all those sets of descriptions are countable because there's only a countable set of Turing machines. Right? There's also many ways to convey an algorithm. I don't know if you remember some 15 years or so ago, there was a DVD encryption scheme that prevented piracy. And some clever hacker discovered just a few lines of code that break the DVD encryption. How many remember that? And of course, they immediately banned this, or at least tried to ban this person from disclosing this proprietary piece of code or algorithm on the web. And thereby, the motion picture industry wasn't very clever. And so they tried to ban him from expressing that code. So, and you could probably actually do that if that code is proprietary. But what they couldn't do is, and what he did is he wrote that piece of code in script on T-shirts. And now it's a piece of art. He wrote a poem that in words, colloquially, describes the algorithm very poetically in flowery terms, but it was very precise. And you can, from the poem, back engineer the algorithm. He created artwork and posters, with flowery, the depictions of this algorithm in all sorts of symbolic, colorful images. And of course, now if they try to restrict him from doing all that, they're banning his free expression and artistic rights. And that they couldn't do. So they looked very stupid trying to do that. And because they tried to do that, all of these images and poems and T-shirts went viral. And now everybody knew them even worse than before because they tried so hard. This is called the Streisand Effect. How many heard about the Streisand Effect? So it goes back to Barbara Streisand back in the year 1999 and 2000. Some entrepreneur, activist, environmentalist rented a helicopter and took high-resolution pictures of the entire California coast from Baja California, Mexico, to all the way to Washington State. You know, images, successive overlapping images of the entire California or the entire coast of the United States. Actually, maybe it was just California. Anyway, Barbara Streisand mansion in Malibu appeared in one of those images. And she had her lawyers sue him to remove that one image from the set of thousands of images of the coast, because she said it breaches her right to privacy and impinges on her security. And if everybody saw that her mansion is there, right there on that cliff, you know, they might stalk her more or whatever. You can guess what happened next. You know, people said, "Oh, really? That's Barbara Streisand's house?" And they posted that picture to 10,000 other websites. And of course, it went viral. And because she tried to sue the guy, everybody made big hay about her mansion, and now it got infinitely more publicity than it ever had before. Before, it was just an obscure house. Nobody knew where she lived, really. And it had the exact opposite effect. Not only that, there's a wiki page now with her mansion picture on it and this description of everything I just told you. And the title of this wiki page is the Streisand Effect, and it became a colloquial term of speech. So now whenever our government does something strange or try to ban something, like when the book Fire and Fury was, the White House tried to ban that a few months ago, it made it a bestseller. That's an example of the Streisand Effect. And it's about to happen to a certain lady that is trying to say what she wants publicly, but the White House is trying to ban her too. And she's becoming famous, and that's just giving more and more. Anyway, so, but I digress. It's a fun story. So Barbara Streisand now is famous in two different ways. She really wished she was only famous for one thing. Okay, so again, the caveat is it applies only to properties, not to other things. And in the book, on page 213, it's described as one of the problems. Problem number 5.28, it says, basically, prove Rice's theorem as a problem. You know, I'm not sure what the author was thinking. I never give you a problem that's that hard to prove as an exercise. Of course, he gives you some hints here, and there is a solution. To his credit, it is a start problem, but there's also an answer in the back of the book. So look at the answer in the book corresponding to problem number 5.28 on page 213, and this will tell you more about Rice's theorem. And of course, there's a wiki page on it and so on. Any more questions about that? So again, here's the Chomsky hierarchy. The regular languages, the context-free languages outside. This is a Venn diagram, set containment diagram. And there's the decidable languages, there's the recognizable languages. These are all proper subsets of their containing sets. But this is a simplified version of these four sets: regular, context-free, decidable, Turing recognizable. Here's my diagram, which contains a lot more information and other sets besides. So sure enough, here's the regular, here's the context-free, right? Here's the decidable, and here's the recognizable. And there's other things here too, and in between, I'm giving examples in green of things that are in one set but not in the other. You've seen this diagram before. It's important that we continually kind of refer to that to see where we are. So for example, properties are subsets of recognizable languages, so they contain elements from this set here, right? And some properties are decidable, the two trivial ones, and most of them aren't. Almost all of them are not decidable. And there's also languages which are not recognizable, so the halting problem is recognizable, but not decidable. So the halting problem is here, but not here. And the complement of the halting problem is not recognizable, because a language is recognizable if and only if its complement is recognizable too. And if a language and its complement are both recognizable, both are decidable. Why? Because you can run both recognizers in parallel on the same input, and one of them will finally recognize, and either way you can stop both when one of them recognizes. And now you're deciding it. You're always halting. How many get that? So, really? Only 10 of you? Okay, maybe I said it too fast. I'll repeat it. So if a language is recognizable, that means there's a Turing machine that recognizes all the yes instances but can run forever on the nose. If the complement of the language is recognizable, that means There's a Turing machine that recognizes the complement, that recognizes the yeses of the complement. That means the no's of the original language, and maybe runs forever on the others. But if you run both recognizers on the same input, one of them is sure to stop and say, yes, I recognize that, I accept it. Whether it's the recognizer for the language or the recognizer for the complement of the language, either way, you stop and you know, which means now you got a decider on your hands that always stops. How many get that? Good. I picked up half the class. That's good enough. So there's the complement of the halting problem, which can't be recognizable by this argument. Right? Because if the complement of the halting problem h bar was in this region here, then both will be in this region. That's what we just said in general. Okay? So again, this is the touchstone for the whole course, this single slide. There's a lot of stuff going on here, and as we're going through this course, we're filling in more and more regions and proving more and more theorems. And speaking of theorems, let's prove in quick succession some closure properties of decidable languages. So again, a decidable language is a language that is recognized by a Turing machine that always halts. So why is the union of two decidable languages also decidable? Not hard. So if you have a language that's decidable, another language that's decidable, the union of them, the set union of these two sets of strings, is also a decidable language. Why is that true? It's easy, but you got to say something, right? Silence is not a proof.
Each one must have a decider, so you just run.
Yeah, each one has a decider, because they're both decidable. So run both deciders in parallel on whatever comes in, and if one of them says yes, you say yes. If both of them say yes, you say yes again. And so you're accepting now the union, and you're deciding on the union, because you know, if both, you only say no if both say no, and they both have to run in finite time because they're deciders, they always halt, and so you just decided the union. How many get that? Okay, so union preserves decidability is what we're saying. Okay, so simple technique, simulation of the two deciders. The decidable languages are closed on the intersection, so intersection preserves decidability. Why? Yeah, you could say the Morgan's law. Let's not be as fancy as all that yet. So what's another way of doing it? Yeah, again, simulation, if you run both deciders, and if both say yes, now not just one or the other. Or you can use the Morgan's law, but when you use the Morgan's law, you need complementation. That's why I kind of hesitated on that. You're right, but you got to show that they're closed on their complement first. And then you can use the Morgan's law based on either one or the other, union or intersection. So complementation is basically simulate and negate, just flip the answer, right? So those are easy, relatively easy theorems, right? Decidable languages are closed under concatenation. That one is not as obvious. Why, if you take a language concatenated to another language, why is the resulting language decidable as well? I mean, it's easy, but not as easy as the first three. What do you got to do? How do you decide whether a string comes from the concatenation of two different languages? Both of which are decidable. And if you can always tell whether it does or doesn't, you are deciding their concatenation, which means concatenation preserves decidability. It's a closure property. Maybe I psyched you out by saying it's not as easy as the first. It's still easy, it's just slightly more sophisticated than the first three, yeah. Yeah, exactly. Beautiful. Take the string, and then you don't know which two substrings concatenated together gave you this resulting string. But you don't have to know. You take all guesses. You take all possibilities of unconcatenating a string into two pieces. What does unconcatenating mean, colloquially? Splitting it into two pieces. But you don't know which two pieces. So you try them all. Try the epsilon and the full string. Then try the first character and everything but the first character. Then try the first two characters and n minus two characters remaining as two pieces. Run both of them through the two deciders for the two languages. And keep doing this. If one of those splits succeeds and the two deciders accept the two pieces, then what do you know? That it's in the concatenation, and you say yes, and you've decided that it's true and you're right. And you try all possibilities. The only time you say no is if none of those unconcatenation splitting operations succeed when the two deciders try to process the two pieces that you unsplit it into. How many see the strategy? Yeah, so we try them all. We're not trying to be efficient here yet. When we're going to talk about NP-Completeness in a couple of weeks, we will do all this stuff with efficiency in mind as well, which is harder. I mean, right now we're just concerned with what is possible, and we already know a lot of things are impossible. We just saw Rice's theorem telling us an uncountable number of things are impossible. So it's amazing we can even add two numbers together at this point. Things are so pessimistic in some sense with respect to decidability. Okay, what about clean closure? How do you determine whether the so the clean closure preserves decidability? If you have a language, you take the clean closure of that language. That's also a decidable language if the original one was decidable language. So clean closure preserves decidability. Why is that true? That's a similar proof to what we just been through. So what we just said about concatenation preserving decidability is you can guess factor the string, i.e. unsplit the string into two pieces. What about the clean closure? Very similar idea, except what's the difference? Take a wild guess. What is the clean closure, by the way? The clean closure of a language is defined as what? If we don't know the definition, you can't solve the problem. Right? What's the definition of a clean closure of a language? Yeah, concatenate with itself any number of times, in any order you'd like. You could take strings from the language in any order you'd like and concatenate, bash them together. So, why do you solve this? Yeah, so unfactor, guess factor or unsplit in some sense. Unsplit the string into all possible number of substrings, not just two, but any number you'd like. There's only a finite number of substrings you can break it up into, including epsilons, right? So break it up into any number you want, and then feed all of those through the decider for the original language. And if the decider says yes on each and every piece, substring piece, you know that all of them together are an element of the clean closure of that language. How many get this strategy? So it's very similar to this strategy here for concatenation, except for unsplitting it into two-piece substrings, you unsplit it into any number, not just two. That's it. That's really the only difference in the strategy. And there are similar properties for recognizable languages. So they're closed under union, again, by simulation, right? They're closed under intersection, again, by simulation. The only caveat here is what? When you simulate two things that are recognizable, you simulate two recognizers, you can't just simulate one and wait for it to give you the answer, and then simulate the other and wait on that. What's the problem with that strategy? It's not guaranteed to halt. So what can you do? The word is on the slide. Run them in parallel. Right? So if you run them in parallel, whichever one halts, you'll know without waiting on the other one to never halt and therefore running forever without running the first that halts. So you can't run one or the other. It's like the venture capital model of computation, right? Venture capitalists never just invest in one company because they don't know what's going to happen. Even if it does happen, it could take many years. They parallel process. They invest on several companies, and whichever one runs away with wild success, they can even shut down the others for all they care. Mission accomplished, right? So use parallelism to avoid running forever. The only thing is it's not closed under complementation. Closure under concatenation, again, you can unsplit and run in parallel into two or more pieces. To do the complement, in general, it's not closed. How do you prove that? Counterexample. The halting problem is recognizable by simulation. You can run a program and know if it halts. If it halts. If it doesn't halt, you don't know. And the complement of the halting problem is not decidable and also not recognizable. Because if the complement of the halting problem was recognizable, both will be decidable, but the halting problem isn't. So the complement is not recognizable. We mentioned that 10 minutes ago, but we're saying it again here. And the only non-closure here is complementation. The other ones preserve closure. the other operators preserve closure on recognizable sets. So we just proved, what, 5 theorems here and 5 theorems on the previous slide. So we proved 10 theorems in 10 minutes. That's pretty good rate. You know, if we keep going like that, you know, we'll prove hundreds of theorems throughout the course. We already proved many dozens, by the way, just if you're not keeping count. All right, so the next homework is due this Saturday, and this weekend I'll also release the midterm. It's not going to be much different than the homeworks in terms of difficulty and scope. There'll probably be 6 or 7 problems. You'll have 6 hours to work on it anytime in the next week or so. So you can pick and choose when you work on it for 6 contiguous hours. It's got to be contiguous. All right, see you next time.